Hello everyone, a very good afternoon to all of you and warm welcome to Multimedia Studio, LNT College Muzaffarpur. Today I have brought more interesting and scientific topic, that is the catalysis, the understanding of Arrhenius equation, right? So the catalysis and catalysts, right? So as you know that there are so many reactions in the kinetics are well known and that are actually creating some products after reactions of some reacting species or molecules, right? Suppose we have two reactants, that is A and B. Once it react to each other, it forms a product C, right? So this is a common and general equation A plus B that forms C. So this is actually, these two are called reactants, right? And this is product. Now these reactions may be either decomposition reaction or it may be precipitation reaction or it may be redox reactions or it may be disproportionation reaction, right? So there are so many reactions are known in the chemistry that occurs to get desirable products, right? So all the reactions does not occur simultaneously, or it will take long time to complete the reactions and formation of the products, right? So suppose A plus B that forms C. The production of C can take 10 minutes or more than 10 minutes or even 1 day, 2 days, 3 days. So depends on the nature of the reactants, right? So if there is no another substance, or you can simply say if there is no foreign substance, then this reactions actually is called uncatalyzed, right? But these reactions A plus B can form product C in the presence of foreign substance. So then the reaction is called catalyzed, right? As you know that rate of any reactions actually depends on this. So this is the concentration of A for a small change dA upon dt, right? And for the reactant B, so that is equal to minus dB upon dt. Here minus sign indicates that after passage of time, the concentration of the reactant molecules decreases and hence the concentration of the product molecule increases. So if there is decrease in the concentration of A, it means dA should be negative and negative positive, and hence rate will be positive. So to maintain the positive rate, we have to explicit this kinetics, right? And as you know that rate of a reaction is proportional to dA upon dt, right? So rate of the reaction will be, that is K, that is actually Kf, rate constant, multiplied by dA upon dt, right? So if reaction goes in the forward directions, right, so then there will be Kf. If these reactions further reverse back, it means the product undergo decomposition to form reactants, then it have a Kb, right? So this is rate constant for backward reactions, and this is rate constant for forward reactions, right? So forward reactions, in case of forward reactions, rate is directly proportional to rate constant, and since this is your negative overall for the forward reactions. Now for the backward reactions, the rate minus Kb dC upon dt. Here minus will be eliminated and it will be positive, right? So for the reactants in a forward reactions, the rate is defined like that, and for the product, rate defined as dC upon dt, right? So here positive sign indicates that after passage of time, the concentration of C is increasing. So overall, this is positive, right? So positive rate constant. Reaction can go in forward direction or reverse direction. So depends on the nature of the reactants and products. Okay. So sometimes reactions does not undergo spontaneously, right? Or you can simply say it will take longer time to complete to form the products. So what happens here? Actually, the term catalysis which is a phenomenon, right? Actually, when a foreign substance is added to a particular kind of reaction, the rate of the reaction or speed of the reactions increases, right, to form the products. So the final products actually look like that, A plus B. So it forms product P. In the presence of catalyst, so on the above of arrow, we can write catalyst. So under the presence of this catalyst, the product P is formed, right? What happens here, we can understand by a graph. So suppose this is your x-axis and this is your y-axis, right? So on y-axis, we can show here energy, or simply you can say potential energy of the reactant molecules. Potential energy of the reactant or product, right? So this is actually progress of reactions, progress of reaction, right? If there is energy level where all the reactants molecule are present, so if this graphs look like that, right? Suppose this is your, and this is your energy of product EP, and this level is defined as energy of reactant, right? So once the reactant molecules are present in this particular level, so and the products which is obtained during the course of conversion of reactants, so this is your energy levels of product. Now this is reactants and this is products. Now, so this height, right? So this is called energy barrier, or simply you can say this is activation energy. And which is denoted as EA, right? Now, if this height is very large, it means energy barrier is very high. Suppose we have the reactants molecules having energy that is ER. So before conversion into the products, all the reactants must reach to this point, right? So suppose this is actually we have to increase the length of this particular axis, right? So this point is called, this level is called threshold, threshold energy or threshold point, right? And the peak of this curve is called transition state, right? So this is transition state, and you can simply say this is potential energy diagram of a particular kind of reactions. Now, so all the reactant molecules does not have sufficient kinetic energy, or simply you can say energy, so that it can reach at this point, that is threshold points. So once the product is formed, then this threshold point should be overcome, and then only this graph flows accordingly to form products. So this is called activation energy, right? And this activation energy is defined as EA is equal to threshold energy minus energy purchased by reactant molecules. So threshold energy is large, right? So this is from this point, this is the origin point. From this point to this point, this is your ET. This is called threshold energy levels. And from this point to this point, this is called energy level of the reactant species. If you subtract this ET minus ER, right? So this is your ET minus ER, then we get activation energy, right? So activation energy is actually defined as the minimum energy required for a particular kind of reaction to yield a products, right? So this is your activation energy. And what is the unit of activation energy? It can be measured in kilojoule per mole, right? So here, once the reactant reaches from this point to this point, right? It means the molecules form a transition state. Suppose we have a reactants A plus B, then it forms A dot 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 B, that is denoted by star. This is transition state. And finally, if this threshold is crossovered, then it ultimately dissociate into product, right? So this is the transition state, and rate of the transition state is equal to, that is rate constant K T, that is rate constant for the transition state, multiply concentration of the transition state. So you can simply say A dot dot B star. So the rate of decomposition of the transition state is directly proportional to the concentration of the transition state and rate constant of the transition state. So accordingly, this transition state can be converted into products. But what happens here? Reaction does not occur sometimes spontaneously. It can take external energy, or some reactions can occur through releasing the energies. So reaction may occur, that is actually endothermic reactions, if you supply the external energy to the reactions, or if the reaction occurs through release of the energy, then this is called exothermic reactions. So reactions may be either endothermic or exothermic depending on the energy levels of the reactants and the products, right? So what happens? You can simply say the enthalpy of a reactions or change in Gibbs free energy. So suppose delta H of the reaction, this will be EP, or simply you can say enthalpy of the product minus enthalpy of the reactant. So this delta H R may be positive or negative, but here EP is lower than ER. It means HP is lower and HR is upper. So overall, the final equation looks like that. So this will be actually negative, right? So this is negative. It means this reaction undergo conversion into products through the release of the heat or energy. So because the change in enthalpy of this particular reaction is negative, right? So this is, you can simply say, from this level to this level, this is delta H. If this reaction occurs at standard state, then this will be delta H naught, right? So depending on the amount and sign of this particular delta H, we can define a reaction may be either endothermic or exothermic. So here the energy of product is lower compared to the energy of the reactants. So ultimately products minus reactants, this will give negative. So this is exothermic reactions. So every reactions that occurs actually involves collisions, or simply you can say effective collisions are required to convert all the reactants into products. So collisions, it means once the reactant molecule reaches this point at the transition point, and if the energy is sufficient or if the activation energy is minimum, then they will collide to each other, they will react to each other, and ultimately it will produce this kind of product P. So this is what is the product. Now this EA is activation energy for the forward reactions. So this is your F EA. In the superscript we can denote F. And for reactant molecules, because here reactants molecule have to reach at this point. So this is actually activation energy for forward reactions. And in contrast, if the reaction is reversible, it means if the product undergo decomposition to form reactants, then what happens actually here? We have to reach from this product molecule to this transition state. So this is called EA backward reactions, right? It means you can simply say delta E is equal to EAB minus EAF. Overall, this will be delta E, right? So if this delta E is positive or negative, it will defined accordingly. If delta E is positive, right? So it is actually gives us endothermic reactions. Endothermic reactions. And if this is negative, delta E is negative, then this is called exothermic reaction, right? So reaction may be endothermic or exothermic depending on the final difference and its sign of the activation energies. So in case of forward reactions, the activation energy of backward reaction is very, very high. So EA backward is greater than EA forward, right? So in case of this kind of plot or this kind of reaction pathway, so this is very, very high. So it means the product is more stabilized, or the concentration of the product is very, very high in the lower energy state. So it's not easy to reach this at this particular point and finally convert it back to reactant species. So because of the height of the energy barriers is very large, so reversible reaction is little tough as compared to the forward reactions, because forward reactions have height. So this height, so the height of this barrier is low, but height of this barrier is very high. So this molecule needs minimum amount of energy to cross over this particular transition point, but this product molecule needs more energy or maximum amount of energy to reach at this particular transition point, and then only it can reverse back to form reactants. So this is what actually the energy profile of particular kind of reactions. Now what happens if we add a catalyst? So catalyst is nothing but we can define catalyst. Catalyst is a substance, right? So that is used to speed up or enhance the rate of a reactions without consuming itself, right? To produce product is called catalyst. So catalyst is a substance which speed up or increase the rate of a reactions without consuming itself is called catalyst, right? So it is specific, right? So this is actually specific, and this is also selective, right? So each and every catalyst has its different role. So for a particular kind of reactions, not every catalyst is suitable, rather it requires different catalyst. So once the catalyst is present in the reaction medium, what happens on the energy profile? So again we can draw, suppose this is your x-axis and this is your y-axis, right? So this is your energy levels and this is your energy level of product. So this is your EP and this is your ER. Now, so this is your flat lines and this is earlier defined as EA, activation energy. But once the catalyst is added, the reaction adopts an alternative pathway so that the products can be produced easily. So what type of alternative pathway actually? So you can simply say this is looking like that. Now the height of this activation energy is reduced. Now it becomes EA dash, right? So earlier the height of this activation energy EA is very large, right? EA is very large compared to EA dash. So such type of profile actually is called uncatalyzed reaction. Uncatalyzed reaction. And if energy barrier is reduced, or you can simply say the peak gets shifted to lower energy side, then such type of profile is called catalyzed reaction, right? If the energy of activation is reduced or height of this particular barrier is reduced, then the reactants molecule can collide easily and convert it back to products. So it will take low time and the products will be obtained as a major products, and the nature of the products depends on the specific nature and selective nature of the catalyst. So catalyst does not consumed in a particular kind of reaction. So it is actually taken in a small quantity or little amount is sufficient to speed up the reactions. Here the role of catalyst is not to initiate the reactions, right? Rather, it will only enhance the rate or speed of the initiated reactions here. So, only a small amount of catalyst is needed to speed up the reactions, because here does not take part in a particular kind of reactions. So, here the transition state is dissociated to form products. So, this is your transition state, transition point. So, before the product is obtained, the reactants molecules have to cross over this particular point. So, only then we can get this product. So, for crossing this particular point, the reactants molecule take maximum energy, or you can simply say it will take more time, and then only we can get the product. But after addition of a catalyst, so the barrier of this height is reduced. Now, this point is a new transition state. So, here this is uncatalyzed transition state, and this is catalyzed transition state. And if this transition state is actually weak, then it will easily decomposed into products, right? So, this is actually progress of reaction. So, the role of catalyst is to reduce the height of the energy barriers, right? Here this height indicates the energy of activation energy is reduced from this to from this. So, the main or chief role of catalyst is to decrease the activation energy of the reactions, right? So, activation energy is reduced and rate of the reaction is enhanced, and finally we can get the product molecules, right? So, this is the beauty of a catalyst. So, catalyst only can decrease this particular energy barriers. So, if multi reactants are actually involved in a particular kind of reactions, so once the catalyst is added, so what happens, it can adopt not only single alternative path, rather it can involve different alternative path of reduced activation energy, and the concentration of the product will be very, very high. So, it can simply look like that. So, now, so this is your uncatalyzed, right? So, this is your look like that. So, here may be two transition points. So, this point and this point. Here it may be only one single transition point. So, different kind of transition point have different activation energy. So, sometimes it have little lower, so it have little higher, it have little lower, and other transition point may also exist by adopting such type of profiles. So, ultimately these transition points are dissociated to get back into product. So, what happens in the presence of catalyst, the reactants molecule to reach at the transition point, and they undergo effective collisions to each other, and it will adopt a different alternative having reduced energy to convert it back into this particular kind of products. So, catalysts have a tendency to reduce the activation energy of a reactant molecules. And if the reaction is reversed back into reactants, then the activation energy will take place accordingly, are required accordingly. Now, any reactions, as you know that delta G is equal to delta H minus T delta S. At standard state, delta G naught. So here you can show G naught. T is the absolute temperature. Delta S naught is the change in entropy at standard state. So delta H naught indicates change in enthalpy of the reaction at standard state, and delta Z naught indicates change in Gibbs free energy at standard state. So if delta G is negative, so the reaction will proceeds spontaneously, and if delta G is positive, the reaction will not undergo spontaneously. So it will requires external energy to proceeds this kind of reactions. So depending on the change in Gibbs free energy at standard state, so the reaction can be converted into products, right? So what happens, how this activation terms actually arise in the next page. Activation energy, right? So EA. So the minimum amount of energy required to a reacting molecules to convert it back into products after a effective collisions, right? So the most important expression, that is actually Arrhenius equations. As you know that this is your Arrhenius equation. So Arrhenius equations, it is expressed as K, that is A exponential minus EA upon RT, right? So this is the most important reactions, most important expressions. Mathematically it can be written as, here K is the rate constant of a particular kind of reactions. So this is your rate constant. So rate constant for the first order reactions, it may be second order reactions, or it may be third order reactions. So depending on the type of the reactions, order of the reactions, actually it can have units, right? And this is your pre-exponent factor. This is pre-exponent factor. Now this is also called a Arrhenius constant. Arrhenius constant, right? Now another term, that is EA. In the previous I have explained about EA. So this is activation energy of a reaction. In kilojoule per mole. Now RT, in the numerator EA activation energy, and in the denominator RT. So this RT actually average kinetic energy. Average kinetic energy, right, of the reactant molecules. In a separate form, R is the gas constant, which have a value 8.314 joule per Kelvin per mole, right? And T is the absolute temperature in Kelvin. Absolute temperature, right? So these are the abbreviations of terms in this particular Arrhenius equations. Now rate constant K is depends on two factors, that is actually activation energy and temperature of the reactions. So as you know that if you increase the temperature of a particular kind of reactions, then rate of the reaction increases, because the after increase of temperature, the energy of the molecules uh, molecules increases, because the kinetic energy means more number of molecules, they will start to collide to each other and they will generate thermal energy in within the reaction medium. So it will have like that. Now this rate constant depends on this factor and these factors. So suppose A, so A is called frequency factor, it is also called frequency factor, or simply you can say collision factors. So A is constant, which is actually collision factors, right? Now this A has, so Z into rho, right? What is Z? Z is called collision frequency. Collision frequency. Now this rho is called steric frequency. Steric frequency. Yeah, you can simply say steric factor. So Z is related to collision factor and rho is related to collision steric factors. So in this way, this value will attain in this particular expression. Now here rho rate constant depends on this exponential terms. So what you know that the rate of a particular kind of this is your T and this is your rate. A particular kind of reaction, if you have a particular kind of reactions, then the rate versus T, so this is rate and this is temperature in Kelvin. The rate of reactions increases exponentially with increase of temperature, right? So if you increase the temperature, the rate constant increases exponentially. But here rate constant A exponential minus EA upon RT. So if you want to increase this rate constant, then we have to optimize this particular exponential value. So minus EA upon RT, right? So if EA is large and if activation energy is high, then exponential minus EA upon RT will produce overall low rate constant, right? If activation energy is low, right? So if second case, if activation energy EA is low and temperature is high. If absolute temperature is high and activation energy is low, then what happens in this particular kind of exponential equations? The value of this exponential will be increased, will be large, and if there is large, indicates enhancement in rate constant. So any particular kind of reactions, actually K is enhanced if EA is low and temperature is high, right? So lower activation energy and higher absolute temperature is required to enhance the rate constant of a particular kind of reactions. So this is the graph of rate versus temperature, where temperature is increasing on this particular x-axis and rate on y-axis, they are increasing exponentially. But in contrast, we can draw a plot. This is x-axis and this is your y-axis. So this is K rate constant, and this is your 1 by T. So activation energy is constant, R is constant, then the rate constant will vary, depends on the temperature. So this is 1 by T. Here, this point, here it is actually high temperature, high T, here low T. So from high temperature to low temperature, right? So this will 1 by T, here from low 1 by T to high 1 by T. Now this rate constant decreases exponentially. The graph of this particular Arrhenius equation look like that. The rate constant decreases exponentially with 1 by T, right? It means at high temperature, rate constant is large. But if you decrease the temperature, the rate constant decreases exponentially. So rate constant directly depends on the temperature. So and ultimately, so this is the negative term. So the graph look like that. Now this activation energy EA. So if this EA is always greater than 0, right? So activation energy is always a positive quantity. So it is not negative quantity. So activation energy is actually positive quantity. It has no zero value. EA should not be 0. If there is any particular kind of activation energy that have a value EA is equal to 0, it means that reactions occurs very fast, or it will explodes in a very short range of time. So if there is a zero activation energy, it means the reactions occurs in a very fast way. And if activation energy is low, so if EA is low, right, it means low, or it means if it is positive, right, then this will enhance the rate of reactions. So the rate of reactions depends on the energy of activations, and rate constant, if this value ultimately attains, that is 1 value, then K is equal to A, right? So if this value EA and RT overall, this ratio and exponential of this value is 1, or simply you can say, if we can get e power 0, then we can get 1. So here rate constant will be equal to the frequency factor or Arrhenius constant. So the unit of this particular kind of rate constant actually depends on the unit of this. So this is your for the first order reactions, it has a unit of second inverse, and for the second order, it has the unit of mole inverse, second inverse. So depends on the type of reaction. For the first order reactions, the rate constant has per second, and for the second order it has per mole per second, and accordingly, so this rate constant can be obtained in a particular kind of reactions. So this is the explanation of Arrhenius equations. So if you want to increase the rate of a reactions, we have to decrease the activation energy by using a particular kind of catalyst, and if you want to increase the rate of the reactions, so we have to increase the temperature so that effective collision may take place, and after effective collisions the products can be obtained, right? So in the another form, we can write this is your rate constant K A exponential minus EA upon RT. So this expression actually for 1 mole of the reactants. So this is actually RT. So if we wish to write here for a reactants for 1 reactants, then it can be expressed as minus EA upon KBT, right? So for a particular reactants, so this is Boltzmann constant and T is the absolute temperature. Here for 1 mole of the reactants, so this is R, that is gas constant. Now we can convert this exponential expressions, K is equal to A exponential minus EA upon RT. So take ln, that is natural logarithms on both sides. So ln K ln A by the law of product of natural logarithms, ln A plus, so ln and base E, then it will be cancelled out, then this will be minus EA upon RT, right? So ln K ln A minus EA upon RT, or simply you can reorganize this term, ln K minus EA upon R, right? 1 by T plus ln A. So this equation look like y is equal to mx plus c. So this is the equation for straight line. So this ln K natural logarithms on base E. So this is m, that is slope. Slope is equal to here m, that is slope, minus EA upon R. So if you have a activation energy and then we can put R value, then we can get the slope of this particular straight line. So how this straight line look like? So this is your x-axis and this is your y-axis, right? So ln K minus EA upon R 1 by T, right, plus ln A. So at this point, so this is your like that, and this is called ln A, right? Now this is your 1 by T and this is your ln K. It means this equation actually produce decreased linear graph, right? And you can get slope on any stage. So this is dy and this is dx, and if you want to get slope, then slope will be dy upon dx, and hence slope will be equal to minus ea upon r. So this is the variation of rate constant in a natural log with respect to 1 by t. So this is actually the graph. So this is what is the actually Arrhenius equations, and its graph that will explains about the rate of reactions with temperatures. Okay, so I understand that the video will be too long, so I can stop here, and I hope this video would be more energetic and compatible to all of you, and you will gain much more information from this video. And I thank again to all of you for listening and watching this particular scientific video lectures. So thank you. इसको ओके कर दीजिए.